I'm Liz Fong-Jones. I am a AWS server. No, I'm not an AWS serverless hero. I am an AWS hero, but I'm an AWS community hero. There we go. But I often talk about serverless. And today we're talking about how to understand what's happening inside of your multi-tenant applications by using serverless. And it turns out that if you use a tool like Honeycomb, you are secretly using serverless to understand your serverless applications because it just turtles all the way down. So what do I mean by that? Well, let me show you the serverless database that we built that winds up also itself using serverless. So that's always fun. All right, so today we're going to talk about how serverless is useful and painful for on-demand compute and how to figure out how much it costs and to attribute it per client. Oh, hi, there are some names I recognize. Hey, Danielle. Cool. So let's talk about what many people use Lambda for. Many people use Lambda for I have an application that gets hit by end users, and I might have an API gateway or something in front of it, and I run my Lambdas briefly, and then they shut down when no one is querying them. Or you might have step functions. There are a million and one different uses of AWS. Someone says they cannot hear me. Everyone else can still hear me. Yes, Alan, you can hear me?
Yes, we can still hear you. Yep.
Okay. So in that case, the problem is local to you. Sorry. Someone should tell them that in chat because they can't hear me telling them that they can hear me. Okay. So many people use Lambda for a million and one different things. But today we're here to talk about how I use Lambda for a custom data store and how I attribute cost inside of that custom data store. So we'd like to optimize our custom data store that we use at Honeycomb called Retriever. Which begs the question, what is Retriever? Aside from a very cute golden retriever, this is my golden retriever. Her name is Flurry. She is adorable, in my opinion. I don't know whether that's universally shared, but in the case of Honeycomb, what Retriever means is Retriever is our distributed column store that allows us to aggregate telemetry events in real time. And when we talk about telemetry events, what do we mean? We mean data that is flowing from people's applications, whether it be data about what your serverless applications are doing or any other kind of application that you're running. So I've been at Honeycomb for about 5 years now, and I am based in Vancouver and Sydney. And I love sharing what my experiences are, kind of pushing the forefront of what serverless can do. So Honeycomb was created to kind of bring the idea of observability to the masses, of figuring out what's happening inside of our systems, whether it be performance or cost. And that means using distributed tracing, similar to using Jaeger or Zipkin. Those are kind of the tools of the past. But today you might use something like Honeycomb to query your traces. So with traditional monitoring, it's like, hey, I've got a bunch of time series and I'm setting up a bunch of alerts. I've got a bunch of pre-configured and pre-aggregated metrics. And monitoring basically pre-aggregates that and kind of front loads the work to digest and analyze it at the time that you generate the data. In contrast, the idea of observability is let's figure out how we can make everything as quick as possible to post-aggregate, to store the data raw, and then to figure out what are we needing to answer on the fly, regardless of whether or not you predicted what it was in advance. And this is particularly useful when you're doing a cost-related exploration, because when you're doing a cost-related exploration, you don't know what you're looking for necessarily when you're trying to figure out, like, why did my bill go up by $2,000 this month? Or what's my top most consuming customer when you might have 2,000 or 5,000 or 10,000 customers, right? Like, you wouldn't necessarily want to create a time series for each customer because that might blow up the cardinality of your monitoring database. So I'll show you a little bit more of this later with regards to kind of how we analyze what our customers are doing. But the kind of core idea is, you can get an idea of, what's running in your system, and then you can slice and dice it on the fly and say, okay, I want to restrict to specific calls. For instance, I want to show only the invoke calls that are at the top of my execution. And then out of all of those invoke calls, right, like we've now set, filter where the service name is Lambda, where it's the top level invoke. Maybe we want to know how fast they run and not just how many of them there are. Okay, so now we have the idea of the P50 execution time of each Lambda invoke. That's kind of cool, right? So that's basically kind of the idea in a nutshell of what we're trying to achieve when we're trying to do real-time analytics is to figure out what's going on, why is it slow, why is it costing a bunch of money, or maybe it's working fine and we want to keep it that way rather than being reactive. So yeah, the core analysis loop is kind of interactively investigating production behavior regardless of where the trail of breadcrumbs leads you. So this is the non-serverless part of our infrastructure, or sometimes serverless, depending upon whether you are producing it inside of Lambda or inside of EKS or somewhere else. And then we index the data and we shovel it into S3. And this is where the magical thing happens because Lambda is infinitely more parallel and scalable than our EC2 instances ever will be. So we can get tens of thousands of concurrency, literally in the span of hundreds of milliseconds, which is a lot faster than we could start VMs. And we don't want to keep tens of thousands of concurrent workers running at all times. So that is why we care very much about Lambda. The other reason why Lambda is fast for us is because after we're finished processing the data to store it by field name, we write those files onto S3, which means that Lambda has access to it. So there's no kind of bottleneck of reading from the hard drive on one single machine or like 2 or 3 machines. Instead, it's reading from wherever the data is stored in S3, which can be very, very fast and read massively in parallel. So when I say interactive, I'm sure many of you have played with tools that make you sit and wait and wait and wait and wait. What I mean interactive, I mean so fast that you click run the query, have a drink of water, it's done, right? 100 milliseconds is fast, 1,000 milliseconds, okay. If it takes 10 seconds, that better be like a really complex or long query. And if you're sitting there 30 seconds, 60 seconds, a minute, 1,000, 100 seconds, like that's way too long. Like that interferes with your ability to figure out what's going on, whether it's a cost exploration or a performance exploration. So that's how we think about the world, and that's how we've architected things with Lambda as the kind of core element of how we do the querying. And yes, it is expensive, but it is not as expensive as wasting people's time, wasting our own time, wasting our customers' time. So that's kind of how we think about it, is how can we pre-process it to make it as efficient as possible for Lambda query. So people wind up writing telemetry data, whether from applications on EKS or Lambda, and that data gets sent in typically open telemetry format to our backend. And then we store it into S3, and then we use Lambda to query it. So originally, when we wrote Honeycomb, the idea was that each machine would store some subset or partition of the data onto its local disk, and you would only get the amount of data that was available on your local disk, and we just have to age out the oldest data when the disks got full. It turns out people want to have more than 2 or 3 hours of data, but to the founders of Honeycomb, this technology that we kind of were creating something similar to, that existed at Facebook before and was called Scuba. Scuba stored the data entirely in memory. So to put it even on local SSD was giving people hours of resolution and not just minutes, right? So that was an improvement, but what if we could do better, right? So one way that we handle that is, doing optimizations like writing one file per column so that you don't have to analyze quite as much data. And then you only have to touch the files that are relevant to the query that you're running. And we also have optimized around querying things that only fall within the relevant time range, right? If I know that this, for instance, I just had a scare with COVID in my household. So I'm going to use some props here, right? Let's suppose I were curious, whether I were sick with COVID last week on Tuesday, right? Here are my COVID tests. Okay, that's fine. That's close enough. Okay, here are my COVID tests, right? Does it make sense to look at the COVID test that I took 2 weeks ago? No, right? Like that's throw it out. Like you don't need that. That's not relevant to the time range you're looking at, right? Like you're only trying to hone into things that overlap with the time range of interest. So we do that. And then you can only query the things that are inside your time range. So when you start increasing the amount of data, suddenly it no longer fits on local SSD, and we decided to tier that to S3. So now S3 is this infinite scalable storage, but now you have the problem of, okay, you've got 60 days of data that are stored on S3. When it comes time to query it, it just takes forever because it's blocking on the, 2 or 4 or, even 16 CPUs of a given local host that's analyzing the telemetry on its local SSD, as well as everything that's in the history of S3. So, yay, now people can run queries over 60 days, but it takes a while. So really the core problem here is we want lots of compute on demand, like my dog. My dog loves to play with all of the toys whenever she wants to play. But then I've got dog toys lying all over my floor and I'm tripping over them when the dog is asleep, right? That doesn't really work so well. So what if we could feed our compute engine lots of compute, but only when people click the run a query button? So AWS Lambda, I can't show you the exact number, but AWS Lambda gives us on the order of tens of thousands of concurrent Lambdas, and they literally can spin it up within the span of hundreds of milliseconds when we need it. So what this actually does is instead of having the data stored in one retriever, we wind up buying it in 1 millisecond units from AWS Lambda. And the very nice corollary here is the cost analysis is very simple because AWS bills per millisecond that your Lambda is running. So the cost is proportional to the amount of, execution, right? If I make my Lambdas faster, they will execute faster and then they will bill me for less time. Whereas, accounting for this kind of steady state base of these like workers running on EC2, that's a lot harder to attribute because they're running flat out all the time. There's kind of no option to scale them in or out, or to say, this one query took this percentage of one of these workers. Whereas I can know exactly how much it's costing when it's running on Lambda and attributable down to the individual customer. So Lambda scales up our compute in that it takes, 50 milliseconds P95 to start up. 90% of them will return within 2.5 seconds. So well within that window of, it'll come back, I'm sure, before I finish taking this sip of water. And per CPU second, it is only 3 to 4 times as expensive as EC2. You would think that this should scare you, but actually, this is actually a very good number. Because if you think about it, if we go back to this graph here, right? And you look at the peak utilization here, the reality is we are getting less than 5% usage of our maximum throughput at any given time. Lambda would be a good deal. Okay, Lambda PMs, please don't hear me say this. Lambda would be a good deal even if it were 10 times as expensive as EC2 and not 5 times as expensive. I'm serious, right? Because you get perfect utilization out of your Lambda. You pay for no more or no less than you need. So sure, if you're running a serverless application and you are running it flat out all the time at more than 50% utilization, use provision concurrency or just flip it over to running in Fargate. But if you are with a bursty workload or intermittent workload like we are, the fact that it's 4 times as expensive as running EC2 flat out, that is a bargain because you do not have a capacity plan. And this is really a secret behind what's helped Honeycomb scale. This presentation deck is now 2 years old, but at the time we had grown by a factor of 10 in 3 years, both in terms of the amount of data that was coming in and in terms of the number of queries that people were running against that data. So why is the Lambda team not jumping up and down and saying everyone should do this? Well, there are some asterisks that I, as a diligent site reliability engineer, have to tell you. First of all, there is an AWS concurrency limit. And by default, this has changed recently. It used to be that you would have to run straight out for something like 5 minutes before you would start getting increased concurrency. Now you get, I think, 1,000 concurrency added per 10 seconds, which is much more reasonable, but still means that if you are trying to scale something up within milliseconds and not tens of seconds, you're going to start getting HTTP 429s when you try to query Lambda, because it's going to say, I don't have that like sleeping and waiting to invoke on a number of different Lambda runners. I need to cold start that. Like, that's going to take me time to do, mate. So, if you don't have that sustained load, then you never wind up scaling past your burst limit. Now it's 10 seconds rather than 1 minute, but still, if you are running queries that ideally complete within 10 seconds, that's not an ideal fit unless you kind of talk things out and work things out with your AWS team. But it's really helpful to be able to plot that, to have charts and graphs to show to people of this is what's happening. This is what my workload looks like, and this is why I'm not being able to get the scaling that I anticipate. So there are limits. Change your retry parameters and make sure you have adequate observability, and talk to your account team. The AWS Lambda team is super, super helpful. They just need to know, what are you doing, and are you creating an infinite loop with Lambda, and do you really mean to spend X $100,000 per month on Lambda? Some other asterisks besides on scale. That's the median startup time. Some functions take substantially longer startup. So in this case, you can see that this function that was running, we have telemetry not just per invoke, but also for the lifetime of the Lambda function. So how long does it take to run the main function and get warmed up? How long does it spend running versus sleeping? So you can see what I meant when I said, we have less than 5% utilization, right? We have less than 5% utilization because a majority of the time our Lambda workers are kept slept on the Lambda runners, right? There's this window of 33 seconds that this one individual Lambda worker was not processing any requests, and then it woke up to run for 614 milliseconds, right? So that's important to understand when you're trying to figure out, how much is this Lambda costing me? Well, it turns out that it's probably costing Amazon something to, keep your Lambda while it's sleeping frozen and in suspended animation. Sure, it might not be consuming any CPU cycles, but it still has to store the state of the RAM of that worker somewhere. So you can see, right, we've got somewhere on the order of, Amazon keeps us cold on up to 30,000 at the time concurrent workers at a time, and then at any moment in time, it will let us just go ahead and flood those workers, right? So you can see when things are quieter, Amazon will scale us all the way into 2,000 slept workers, and then when you hit peak usage, right, it'll go all the way up. So the other thing was, 90% return within 2.5 seconds, but you don't want 10% of your data to be missing. So what happens to the other Lambdas that don't return within 2.5 seconds? So that's what this band here is. And unfortunately for us, we also pay for all 30 of those seconds of execution. It happens very rarely, but it is the case that sometimes Lambdas never return and they time out at 30 seconds. That's not great, right? Other facets here, functions accept JSON. They don't accept protobuf, at least for now. I keep on harping on the Lambda team. Please support arbitrary binaries. We shouldn't have to base 64 encode our stuff, and shove it in a JSON blob. So there are ways around it. You can shove the data in S3 and send a link to all of your Lambdas to access on startup. Conversely, you can produce an S3 file as output if the output is too large for the size of the Lambda. So again, put the data in S3 and shove it in a link. And, we have data to substantiate that, we sometimes have the output of our processing Lambdas be in the hundreds of megabytes. And the other thing that we do here is impatience. If something is in the slowest 1% of Lambdas that are executing for a given query that our users have run, we just rerun it. In fact, I'm pretty sure I actually might try to live demo this because I know we have a full hour for this webinar. We can actually compute how much of our spend is on retries of that slowest 1% versus of the original 99% that executed successfully. But yeah, basically, even if one Lambda fails, because, S3 wasn't available or just got stuck somewhere or like got lost in the ether, chances are very, very, very good that if you rerun the query, it will not get stuck for the same input. So you just, let them race, right? Like that's literally the idea of impatience, is you let your slowest queries race each other and just see which one returns first. Okay. And finally, as I was saying, this is kind of the meat of the cost reduction and cost attribution piece that we're going to talk about today is, yes, that 3 to 4 times, it can seem daunting. And it is very possible. Early in the history of Honeycomb, before it was routine for us to spend hundreds of thousands of dollars per month on Lambda, early in the history of Honeycomb, we accidentally ran up a $10,000 Lambda bill. That was because we were testing a new alerting function, and that alerting function was reaching back into the past 2 hours of data and rerunning the past 2 hours of data every minute. It turns out that kind of gets expensive. Or if it's not running the past 2 hours of data, if you're querying 30 days of data every minute, that winds up querying the same data multiple times, and it winds up running up a very expensive bill, or what seemed like a big bill for us at the time. So it's important to understand how much is this costing. So this is literally what I mean when I say attribution per client, right? So we have a function that basically a kind of inline transform that transforms the duration of an invoke request and transforms it to the actual dollar amount that we expect to see on our AWS bill. And we have reconciled this, and it comes within 5%, which I think is pretty amazing. That the sum of the amount of time that your telemetry measures your invoke request is running for, if you multiply it by any EDP discounts that you have and the list rate of Lambda, you'll get something that comes within plus or minus 5% of the actual bill that you're charging at the end of the month. And then, in our case, because we're appending lots of custom telemetry, right, we are setting a custom field. So we're not just seeing, hey, this invoke request came in for this specific Lambda function name and function version. We're also capturing information from the request, like who requested this. So again, we're able to attribute per tenant what each Lambda costs, and you can see, some of our customers are costing us, were costing us at the time that we created this, which was 2021. Some of our customers were costing us up to $800 per day of Lambda, right? And I was like, okay, I can reason about this. I can look at the maths and see, how much is this customer paying us versus how much are they costing us in Lambda, and take the appropriate measures. So you can set alerts to say, alert me if any customer exceeds the threshold of $500 per day, and then accept customers that we know are going to run higher than that. But another cool cost thing is you can have, if you're flexible about what CPU architectures you run, you can make things cost substantially less. So in September 2021, Lambda functions on ARM launched that were going to let people get 34% better price performance. Now, if you look at the pricing, it doesn't say 34% cheaper. It actually says 20% cheaper. So we have to talk about what gives. The answer is Graviton processors in general cause your functions to execute about 10 to 20% faster, and they cost 20% less per CPU second. So if you multiply that together and you squint, you get that 34% number that AWS is averaging. But it's not a straight conversion, right? Like it's not necessarily a guaranteed your thing will cost, 20% less or 30% or 50% less. It might be your function runs much faster on ARM, right? In that case, you might get better savings than 20% or 30%. You might get 50% savings. Conversely, if your function is not well optimized to run on ARM, you might only see 10% savings, or you might see it being cost neutral. So we originally got early access to Graviton 2 instances running on EC2. And we found we were able to scale in our ingest fleet. And that's how we realized cost savings, right? Was, because on EC2, the controls that you have are how many workers that do you have and to what extent you scale them up and scale them down. With Lambda, it's all about how long does this thing run for, which means you'd better not be blocking on external processes. Otherwise, you're paying that per CPU second cost, whether your CPUs are being used or not. So this is the kind of analysis that we did to validate whether ARM64 lambdas were right for us, having determined that ARM64 EC2 instances were great. And unfortunately, what we initially found was that we were running A/B tests. We were running 50% or 30% A/B tests of ARM versus x86. And you can see that the latency was initially for us quite bad. And all of the savings was being washed out from it costing less per CPU second or per CPU millisecond was being washed out by the function invocations, taking sometimes up to 50% longer. That's kind of a problem. So we had to go back to the drawing board, and we had to use feature flags to turn that experiment back off and say, like, it's a worse experience for our customers. It's costing us extra money. Like, we need to take a step back and see what happened and why. So fortunately, we were able to literally, look at the timestamp. The feature flag went into effect at 6:48 p.m. local time, and literally within 20 seconds, I turned off the ARM executions back down to 0, and we were running 100% on x86 lambdas. So we were able to get to the bottom of why it was 50% slower, and it basically boiled down to, it turns out the servers actually do exist in serverless. They exist on the Amazon side. And if you hammer the heck out of a brand new announced product of Amazon's, they're not necessarily going to have the capacity available to support you executing tens of thousands of concurrent workers. So our workers were queuing against against each other, and were CPU contending each other on the same host. We needed to upgrade our version of Golang, and we had to do some hand assembly optimization of one of the libraries that we were running that was assembly optimized for x86, but was not for ARM. So these are the kinds of cost explorations that you kind of, wind up getting into the weeds into if you are running up a several $100,000 a month Lambda bill, because efficiency is so key and understanding what your customers are doing is so key. So we were eventually able to, turn it on, turn it back off, turn it on. And eventually, so by October 2022, we were at 95% ARM after some false starts. And then, I can say now that we are running 99% ARM. We only have a 1% x86 holdback just to make sure that we are capable of running an x86. It's not that there are any problems with ARM for us. It's just that we prefer having the flexibility. So the only way to make sure that you never break it is to continuously regression test it. So this is kind of what's cool, right? We're able to use these analytics to kind of smooth out and figure out, okay, what do we need to do to bring the latency? So in this case, purple line is ARM now, right? What do we need to do to make it so that, the 99% of requests that run on ARM versus 1% of requests that are held back on x86, how do we make them perform similarly, not necessarily identically? And also, one of the cool things that we're able to do here is, when I said earlier that that the x86 workers are typically like 20% slower than the ARM workers, and that's kind of how you get the 34% cost savings. In our case, we decided actually to take away CPU and memory. So the x86 and ARM workers have about similar runtimes, but we've actually taken away 20% of the vCPUs and 20% of the RAM off the ARM workers. So that's how we get to the, yes, we're able to validate and achieve the roughly 30% cost savings. So, yes, do this at home with some asterisks. Workloads that are batch processing can very successfully run on Lambda. If you have kind of state that's been moved off of local machines onto S3, you kind of have the ability to create work units. I do understand that there is a kind of batch processing step functions like thing that that will handle this map producing for you, which is kind of cool. But at the time, we wrote it ourselves. But if you're running any kind of like batch workload that's not waiting in real time for users, where a user is sitting waiting on the line, you're better off not paying that 3 to 4x cost, because you can spin up a collection of Fargate workers or spin up a collection of EC2 batch workers. It'll take you 5 minutes to spin up 100 machines, but then you can run those 100 machines for 30 minutes, and then you can turn them off, right? Like, so if you have some kind of workload that's more suited to, I need an answer in an hour, don't run Lambda flat out for an hour. That's going to really make your CFO mad. Similarly, avoid tiny workloads. If you could just answer the question locally or via fetching it from S3 yourself in less than 100 milliseconds, like, don't bother reaching out to Lambda. And as long as you clearly state your intentions to air traffic control or your cloud provider, they're willing to accommodate you. And actually validate to make sure that you understand what's going on. So nothing matters unless users are happy. So that is a very happy golden retriever. So now let's switch to the live demo part. So I'm going to page over to here and show you a couple of things. So let's reproduce that query that I was running a moment ago, or that I showed you at the beginning. So name is invoke, service name is Lambda, and let's group it by tenant ID, and let's show you some of cost. So this is now a live look at 2 hours of data. And you can see that we have one customer who is very well known to us, but I'm not going to name them on stream. But here's an opaque ID number, right? So environment ID 19942 consumed $821 of Lambda over the past 2 hours, and this is something that we believe is worthwhile to afford that customer a good experience, because if we slowed down the performance of that for their engineers, they have thousands of engineers who are using Honeycomb on a monthly basis. So when you have thousands of engineers who are using Honeycomb, if those thousands of engineers are waiting, 30 seconds, a minute, 2 minutes, 5 minutes for their results, that means they're not able to debug things as quickly, right? So we view it as very much worthwhile to do. Oh, I should probably sort this by cost and not by a number of queries, because not all queries are created equal. So let's have Lambda cost ascending. And let's go ahead and filter out those two big customers there, since I know who they are. So environment not in, something like that should do the trick. So now that we filter out those two big customers, right, you can see a majority of our usage is relatively small, and it's going to kind of vary from hour to hour. So this kind of visibility, I think, is really, really awesome for understanding, like, where should I spend my time in talking to people, right? Which customer should I talk to? I should probably talk to those top 2 customers, but let's zoom out and look at, I don't know, 7 days of traffic now. Let's see what the behavior of my largest customers over the past 7 days is, right? So you can see, there is a customer that has cost us $1,000 over 7 days. And interestingly, it looks like a majority of that usage actually was something that happened specifically on April 3rd, right? So I might want to dig into that. So I'm going to run that query, and I'm going to zoom in. So you can see that bit where I'm like, 10 seconds is like, it's tolerable, but it's not great. How long did that actually take? 6 seconds, right? Like, I have high standards now, right? Like, because I'm used to being able to debug the performance, and I care about the performance of what I'm doing, because it's kind of in that critical feedback loop for me. So, but yes, I can zoom into this, right? And I can say, show me what happened with that user in that time range. And now this runs much quicker, right? This runs in 3 seconds because I'm not scanning quite as much data, right? And then now I can see, okay, this individual query here, this looks like one user ran a query that cost us like, $50, right? What's going on with this one query here? And then I might say, okay, show me this individual trace. I want to see what happened in the execution of this. Right, so I think this is what is particularly cool and interesting about real-time debugging and real-time cost attribution per tenant is when you feed your observability system the right data, or in our case, right, like what you're looking at is our dog food environment, which understands what's going on with our production users, right? So we have this kind of meta monitoring. So our meta monitoring environment is super interesting in that it lets us, oh, that's fun. This trace contains 1.5 million spans. That's very fun. So I'm going to collapse everything at this depth, so you can kind of get a feel for what's going on here, right? So I've got a bunch of stuff that executes locally for 30 seconds. And then, yeah, there's going to be, where's the Lambda? Okay, so I probably have to slide this over. Let's show service name. Oops. Wait, that's sortable now? Oh, no. I got very excited for a second. Okay, the Lambda executions are not at this depth. So I need to, as I just said, we need to go deeper. Let's see if I can find that Lambda execution. Oh, well, all of these have various attributes named Lambda. That's not super helpful. Fetch partials from Lambda. Oh, it's like omitted 2,676 spans. So the Lambdas are inside of here. Okay. Slight live demo fail, but that's okay. So yeah, this is what I think is really, really awesome is that kind of visibility. Okay, so there's another way to visualize this data if the trace view isn't doing what I need to, right? So you can see what I mean when I say, right, like Lambda can scale up and scale down literally within the span of milliseconds, right? This here is a 50 millisecond chunk. So you can see that we went from completing 280 requests per 50 milliseconds to 949 requests per 50 milliseconds and peaking at, something like 2,300 requests per 50 seconds. I think it's safe for me to show you concurrency here. Yeah, so you can see here that, for a brief period of time, we had run something like 30,000 workers in parallel to process this one request. And the other thing that I can do with this is I can go and look at the raw data. So you can see when I'm talking about adding keys and values to your data, what I mean is you're able to see information like, which version of Amazon Linux is this running on, in case there's some kind of a performance difference. Actually, that's an interesting question. Let's ask the question, has performance gotten better or worse with different Amazon kernel versions that are running on the Lambda workers and Go runtime versions? That seems like that might be an exciting question, right? But you can see I've kind of decorated many different attributes, right? So I've decorated the values of feature flags. I've decorated the tenant ID. I've decorated in which build it's running, the name of the Lambda function, and all of these. And oh, here's the Lambda request ID as well. So if you want to cross correlate to X-ray, you can do that too, right? So in this case, it happens to be data about a telemetry and observability system, but you could do this with any system that was based off of running large numbers of Lambdas, is to populate this metadata so you can understand per tenant and so forth behavior. So let's actually do what I said. So we're going to group the P50 of duration. Actually, no, I do want the count in case there's a data point that turns up only very, very briefly. So let's group it by global kernel version and global Go runtime version. And let's run it over 14 days. It's possible this will turn to be a dud because Amazon hasn't updated the kernels on their workers, or, oops. Oh, hey, look at that. That's exciting. Oh, I bet, no, the ones here. Oh yeah, these are right, you can see these are the x86 workers, right? Because the kernel version has x86 in it. So if we filter only where the filter only to my ARM64 workers, remove that 1% holdback from our experiment set. Oh, okay, there we go. Oh, that's fascinating. Look, right there. Right there. See that? Amazon were cheeky. Amazon were running the 220.852 kernel on our Lambdas, and they briefly trialed running the 855 kernel, and then they took it away and put back the old kernel, and then finally they've cut over to the new kernel. Similarly, over here, there's something going on with some older kernels that are in the 4.14 series. Fascinating, right? So it's not just tenant ID that you can group by when you have analytics like this. It's also, you can see when the matrix is changing out from under you, which I think is super fun. I need to go and talk to my Amazon account reps and Tam about this. This is fascinating. That so the question is twofold. Are we seeing different performance between the two kernels in the same series? And also, are we seeing different performance between the kernels, between the 4.14 and 5.10 kernels? I've just uncovered a new performance dimension that I didn't even realize that we had. I'm geeking out right now. Awesome. But yeah, that's the live demo. That's the presentation, and I think we've got 15 minutes for any questions that people have about how to do this and whether it's worth doing it, and how, and anything else kind of serverless related.
Yeah, good stuff.
That was awesome. I think I liked the whole presentation, Liz, but honestly, my favorite part was how excited you got looking at that like canary deployment of that Go kernel. That's all. That's pretty cool.
That's Amazon changing out the Linux kernel on us, right? Our Go version stayed the same. Like, sure, we were pushing new release artifacts, but man, that's exciting.
How does somebody get started with Honeycomb? If I have something out there right now, because honestly, your presentation was super good. Maybe you want to try it. How do I start?
Open telemetry. So you add the open telemetry Lambda layer, and that basically sets up a sidecar to your Lambda that will receive the telemetry so that you don't have to keep running your Lambda waiting to offload the telemetry. So you can just say, I want to report, that this request ran, and then it gets sent to the sidecar, and that, gets sent off to Honeycomb after your request is finished. So open telemetry Lambda layer, and then inside of your application, you can add the open telemetry instrumentation to basically have it automatically, let you know when you've received a HTTP call inbound, right? That's an invoke. When you have issued any other outbound calls from your Lambda. So kind of getting started with the auto instrumentation is the best way, and that's going to depend upon your language. It's very much easier in Java, Python, Ruby, anything that supports runtime monkey patching. But if something is C++ or Go, that's going to require you to do a little bit of work to kind of add in the calls to the SDKs.
I want to come back to runtime monkey patching because I've never heard that before, but I'm going to give Brian an opportunity to ask his question.
Really appreciate it, Alan. Liz, this was awesome. Of course, I joined a few minutes late, so if you covered this early, you can yell at me and I can go and watch the recording later. But when it comes to collecting some of the dimensions around customer usage, do you have customers include that in traces, or like how is that metadata being captured?
Yeah, so you could pass it in baggage in the traces. So that's a slightly more advanced OpenTelemetry thing where baggage allows you to propagate information along with the trace and the trace ID. The other option is if you're, naturally including that information as part of the work that's being done, you can pull it out and report it as a dimension, right? The core idea behind distributed tracing is something like, let me just pull up the OpenTelemetry documentation. It'll make that a lot easier to understand. So here, let me share this real quick. There we go. Right. So when you have instrumentation, right, like you'll have a trace span that you've created. And one thing that you might do is you might set attributes on that, right? So if you have things that are inside of your requests, you can pull that data out of the request body and then attach it as an attribute to the currently running trace span. So that kind of is a mechanism of ensuring that any relevant data that you might feel tempted otherwise to log instead winds up being contextually attached to the Lambda execution, and then that enables you to do things like go fetch the go fetch the value of any child spans that have a customer ID set to X or stuff like that, right? Because it lets you scan not just the current line of the current log line, but anything that occurs in the trace hierarchy.
Gotcha.
So, yeah, basically, maybe Go is not the best example of this, but right, like the documentation of, let's see, where is create span attributes? There, okay, right, like again, Java makes when you kind of sprinkle that kind of stuff throughout.
Yep. Okay, that makes sense. Awesome.
We have another question from Praveen. Praveen, you can either say it or you can type it out and I can say it for you.
No, I'm good, Alan. So, hey, Liz, that was a great presentation, and seeing the graph, I was loving it, how the telemetry is looking. So, my question is, like, we have over a million requests coming through the Lambda, as you're showing. Does it impact any performance or cost on the overall process if we include this one into our Lambda invocations?
That is a great question, and I love to get questions like this because you can actually measure the impact of your instrumentation. So let's go ahead and pull up my profiling tool and go look at the behavior of my Lambdas. So if I look at, let's look at 24 hours of data from Lambda. So let's see. So first of all, let's verify that there's very little profiling overhead, and indeed there's almost no time, right? Like if I ask it for backtrace, it's pulling up regex backtracking, but not profiling symbolization. Let's also search for OpenTelemetry. Nope. Yeah, the answer here is Beeline. Okay, there we go. This is using our older tracing library that predates OpenTelemetry because all of Honeycomb predates OpenTelemetry. So this is a older application, not instrumented OTel. But yeah, it looks like. Let's see what's calling. Okay, let's also search for libhoney while I'm at it. Table and find that. 0.34%. Yeah. The overhead of this is less than 0.5%. So my personal view is that we've saved far more money with tracing to understand, like, where's our time going and where's our Lambda's getting slower than the 0.35% overhead of transmitting this data.
Yeah, that's cool. And one last question. How do you report, like if I'm using Honeycomb, right? I used other tools like telemetry tools. They do report us through emails and SNS alerts. Do we have some kind of alerting mechanism in case if I miss it?
Yeah, sure. So, a observability tool like Honeycomb or any other open telemetry compliant backend, right? Like, I was demoing how Honeycomb uses Honeycomb, but none of this stuff is specific necessarily to you have to use Honeycomb, right? I'd love it if you did, but, I try to stay on that good side of the, of avoiding vendor pitching. But yes, Honeycomb does have triggers, right? And SLO burn alerts. So you can send that data out via PagerDuty or Slack or email, right? Like, so any reasonable observability provider will let you, right? Like, in fact, I was showing you that alert that we have if any one customer exceeds spending $1,000 per day on Lambda, right? That's that goes out via Slack alert to our teams. And yeah, it is definitely turtles all the way down, Andres.
Liz, can you go back to the, what'd you call it? Jungle monkey thing?
Monkey
You said
patching.
what is it?
Monkey patching.
What is that?
Monkey patching is when you reach into the innards of the running code and you are overwriting function executions, right? So it's a mechanism in dynamic languages like Python and Java and Ruby, where you can basically say, instead of directly calling the HTTP or XML HTTP library, right, like to go and like issue an outbound HTTP call, it'll first call the OpenTelemetry wrapper around it, right? So you can tell the runtime override this function with something that you weren't originally compiled to do, right? So that means you don't have to make any changes to your code in order to get the benefit of this automatic trace span creation. It's a trade-off, right? Like every language has trade-offs. And if your language allows monkey patching, right? If your language allows dynamic function overloading, it is, it is a performance impact. It is slightly less secure. But the upside is that, it's magical. It just works, right? Like this is how a lot of, telemetry and instrumentation hooks work. This is how a lot of, how you can, add OAuth authentication to every endpoint automatically, right? Like, that Okta or whoever will sell you, you don't have to change your application. We'll just, proxy and gateway things so you can, your applications are automatically protected, right? Stuff like that, right? Like it requires it means that your code is not a fixed artifact because the runtime that it runs in is capable of transforming and modifying it and kind of applying these hooks. So, I, as someone who really loves determinism, I am saying monkey patching in a slightly derisionary way, right? Like in a derisive way, because I'm like, this makes a thing like, not behave exactly as a hermetic binary. But it's useful, right? And I find it hard to argue with that, right? Like, and you can choose what you allow to kind of override your runtime and override your function invocations.
Hey Liz, what was the result of that rabbit hole into Linux version? It looked like the latest version was slower.
Yeah, it sure did look like Amazon rolled out a new kernel that was slower at P50 for our use case. So now I need to go and ping Amazon to find out what's in that new kernel that slowed it down. I don't know. This is a thing that I am seeing for the first time. I just saw that attribute, thought it might be interesting, and ran a group by, and I'm now alarmed enough that I'm going to talk to my account rep.
Can you circle back and tell us what you find out?
Oh, I may or may not be able to tell you that. They like to share information with us under NDA when we when we file support tickets like that. I will tell you if I get to find out, but I think that is now a new piece of advice I will be giving people, which is Amazon automatically updates your runners. Therefore, you should be aware.
There's an insight right there.
Right, like it's all
Okay,
magical,
so-
right? Like you don't have to worry about patching your, Amazon Linux too, because Amazon handles it for you. Because you're just uploading a binary or some code, but it turns out, spooky effects at a distance, they happen.
Now, don't they have an option to turn that off? You know what? We shouldn't get into that. It's with 1 minute left to go. But are there any other questions from anybody before I wrap us up? No? Okay. Thank you, Liz. This was super interesting. Really, really cool presentation. Appreciate the time and the effort and all the
there's
lessons.
going to be a part 2. There's going to be a build on AWS Twitch stream, I think, in 2-3 weeks. So you should definitely stay tuned for that.
That's right. That's on the SaaS Factory with Bill Tarr. Is that right? Yep. Awesome. You can promote. Happy to promote that when we get the links for that. So that was our second SaaS focused talk for the month. Next week, back at the regular date and time, we have Khawaja Shams from Momento talking about multi-tenancy at scale. So he's gonna cover both how AWS does large scale multi-tenancy and I'll give a little peek at how Momento does it as well with serverless SaaS. Really interesting. It's a really interesting talk. I'm excited for it. So again, that's next Thursday at noon Pacific, I believe. So we'll get that sent out. But it's great seeing everybody. Thank you. Good conversation. And we will see you next time. Thank you, everybody.